Okay, after having discussed about electric field and electric potential, the next important topic is Gauss's law. But before coming to the Gauss's law, let us understand the flux, what is called an electric flux through a surface. You have seen here, I have drawn here a simple diagram. There is a small area delta S. This is a hypothetical surface through which electric field is passing and which is making an angle theta with the perpendicular of the surface. So this any perpendicular which is going outward from the surface is considered as a positive outward normal, and any normal which will be going inside the surface will be considered as a negative normal. So E is called as the electric field. So with this we can define the electric flux delta phi. Delta phi is a small electric flux passing through a small area delta S, which is given by E delta S into cos theta. E delta S into cos theta. But as we know from the definition of the scalar product, if A dot B is there, then it is given as AB cos theta. So here delta S is also a vector, E is also a vector. Therefore, we can define delta phi as E dot ds. E dot ds. And what is the direction of delta S? Delta S, the direction of the area vector. This is called as area vector. It is always along positive normal to the corresponding surface. So, positive normal is I have defined here. So, it is going outward from the surface. So, this will be the direction of delta S. Now, cases, there are different cases. If you know that delta S is outward normal, which you can see here, it is outward normal. This is outward normal, and then if E is passing parallel to the surface, then the angle between the positive normal and the electric field will be 90 degree. If this is 90 degree, then you can see that delta phi is equal to A delta S. The electric flux through the small area, which we have already defined as dot product of delta S and E, which is E delta S cos 90 degree. But the cos 90 degree is 0. Therefore, when the electric flux is running parallel to the surface, then total flux will be passing through the surface is 0, and we write delta phi is equal to 0. We will make use of this concept, whatever I am explaining here, along the, that is perpendicular to the electric field. If it is running perpendicular to the surface, if it is running parallel to the surface, we will utilize them to find out, to solve some of the example which I will cover further ahead. Now we come to the case 2. If E is along the positive normal, if it is along the positive normal, means E is perpendicular to the surface and going outward. So here in this case, delta S, we already know it is along the positive normal. So it is positive normal. So delta S and E are in the same direction. So theta between them is 0 degree, and we say that delta phi is E dot delta S, which is nothing but E into delta S, simple, because cos 0 degree is 1. Similarly, if E is in the opposite to the positive normal, means if E is going inward and delta S is going outward, the angle between them will be 180 degree, and we call delta phi as minus E delta S. Okay, so it will be delta phi will be in the negative direction. Now, using the techniques of the integration, if I have to find out for the entire surface, so phi will be E delta S. It is E ds. So I can write it as S. So phi is equal to E ds. So this is an integration size, and this is the formula generally being used to find out the flux through a surface. And if it is a closed surface, we will use the sign like this. So the electric flux is defined as E dot ds. We will make use of this to solve the Gauss's law. Now, before coming on to this, after having explained the flux, I will come to the solid angle. What is a solid angle? You can see here it is it's a surface. It's a surface. So through this surface, it is making an angle at a distance r. If there is a center here, I defined it as O. So this surface is making an angle here. this angle is being made here. We call it as solid angle. Omega. Donation is like omega. Notation is like omega. So the solid angle is defined as S upon R square. You must remember this formula. S upon, it has a sign of, S is a area. R square is also having a area. It is having the L square. And this will also be L square, dimensional analysis. So this angle has become a dimensionless quantity, which is almost similar to if I use a two-dimensional figure. So delta theta will be nothing but arc upon radius, delta L by R. We know this. So same principle is being used for the solid angle. It is area upon R square. Similarly, we know that if this is making an angle, if delta L is making an angle with respect to the R, which is alpha, then delta theta, that is the angle between them, which we call in a two-dimensional plane, is delta L cos alpha by R, because it is a dot product. So same is the case here. Same is the case here in a solid angle. In a solid angle, if R and delta S are in the same direction, then I can say that the solid angle delta omega will be delta S by R square. But if it is making an angle alpha, then delta omega will be given by delta S cos alpha by R square. Here the angle between R and delta S is alpha. Okay. And one more thing which you should understand is that if there is a complete sphere, so the surface area will be 4 pi R square. You know that the surface area of a solid sphere is 4 pi R square. So I am substituting the value for a whole angle. If I have to find out the omega value, what is the solid angle of a sphere at the center? It is 4 pi R square divided by R square, which is nothing but 4 pi. So you must understand and know these fundamental things before we come on to the Gauss's theorem. One is the which I have explained. One is the flux, electric flux, and the second part is the solid angle. These are solid angle. Now Gauss's law now states, after having understood, the Gauss's law states the flux of the net electric field. The flux of the net electric field through a closed surface equals the net charge enclosed by the surface divided by epsilon naught. So we know that this is the total flux through a closed surface. This is the total flux through a closed surface. We define as phi. We can write here as phi, which is equal to q upon epsilon. Okay, so this is Gauss's law. So what is the proof of the Gauss's law? Proof is, we have a spherical surface. There is a point O, there is a point O at which a charge Q is placed, which I have shown it from yellow, and I have to, and there is a point P. There is a point P. So we know now this yellow surface is a Gaussian spherical surface. Now in this figure, a charge Q is placed at the center O, and we have to find out the total flux through the spherical Gaussian surface. So how do we find out? Now we know that the electric field at a point P, which is at a distance r, is given by 1 upon 4 pi epsilon naught q by r square. You can refer to my video where I have covered this topic in electric field. So you can find this will be 1 upon 4 pi epsilon naught q by r square, and most of you know must be knowing that if there is a charge q, so the electric field at a distance r is given by this formula. So now as per the figure which is given above, so delta phi, that is the small flux, the flux to the small area, which I have done it from the green pen. So delta phi will be E dot delta S, will be nothing but E delta S cos alpha, because there is an angle alpha between the positive normal and the E, which I have explained above. So E value is Q upon 4 pi epsilon naught R square delta S cos alpha. So I have separated out delta S cos alpha by R square and Q upon 4 pi epsilon naught. You know delta S cos alpha by R square, which we have already explained, is nothing but delta omega. That is a small solid angle which is made at the center. Which is made at the center. So small flux, so the flux to the small area delta phi will be given by q upon 4 pi epsilon naught delta omega. Now to find out for this entire spherical surface, I am integrating it. When I am integrating it, and I have explained earlier also, for the solid angle subtended at the center of a spherical at the center of the spherical surface is nothing but 4 pi. So it will be q upon 4 pi epsilon naught into 4 pi, which is q upon epsilon naught, and is the right hand side of the Gauss's theorem. So this is the proof of the Gauss's theorem, for which you must know what is electric flux and what is solid angle. Okay, we must remember in this Gauss's law that Q is a charge which is enclosed inside the Gaussian surface. So outside charges will not constitute the flux. Only the inside charges of the Gaussian surface will constitute the flux. And the second is the Gaussian surface is a hypothetical surface. It is an hypothetical surface to solve the problems. Now we will make use of the Gauss's law to find out the electric field due for some discrete and continuous charges. So we will cover the field due to an infinitely long charged wire. You can see here there is a charge wire which has a charge plus plus plus. So charge density is lambda per unit length. Charge density lambda per unit length. So I have made a cylindrical Gaussian surface in which I have broken it into three surfaces: S1 one end, S2 one end, and S3 is the curved end. So the cylindrical charge enclosed, and the charge enclosed in this length L of the Gaussian surface, which is an hypothetical surface, is given by lambda into L, because charge density is lambda per unit length. So lambda into L will be the charge enclosed by this Gaussian surface, which you must remember. Now the total flux for this Gaussian surface will be flux through surface S1, flux through surface S2, and flux through surface S3. Now what the fundamental which I explained, that E dot ds1 for the first charge, because E is running here, see the electric field is going outward. See, E is running parallel to S1 and S2. So E is running parallel to S1 and S2. The angle between them will be 90 degree, and therefore there will be no flux which will be associated with two surfaces. And this I have explained here also. You can just refer to this case. You can here refer to this case here. There is a case in which it is 90 degree. Which case? Yeah, this case is 90 degree. So here you can see that the flux is 0 because cos 90 is 0. So the two end surfaces of the cylinder will not constitute any flux. The only flux which will be passing through will be the curved surface. For this curved surface, as you know, theta is 0 degree because it is going perpendicular. It is everywhere E is perpendicular to the curved surface, and S is outward. You know that S is in the along the positive normal. So theta is 0 degree. So if I solve this integration, I will get E dot ds, and if I integrate the entire ds3 area, which is nothing but the total curved surface area. For a cylindrical, it is given by 2 pi r into L. So when this value is substituted, phi is equal to E into 2 pi r L, and from the Gauss's law, phi is equal to q upon epsilon naught, which is lambda L by epsilon naught. So I have equated these two. These two are equated, and we get lambda L by epsilon naught is equal to E into 2 pi r into L. So E value, which is electric field at a distance r, because of the infinitely long wire having a charge density of lambda, is given by lambda upon 2 pi epsilon naught r. The same I have solved through the basic fundamental of electricity of the electric field by a discrete charges using the integration method in my previous video. Now the second most important and interesting example for having a better understanding of the Gauss's law is, suppose a charge is enclosed in a hypothetical cube at its center. What is the electric field through each face? So here I have made a charge q which is inside a cube. It is a Gaussian surface, hypothetical surface. So I am using the Gauss's law. E dot ds is q upon epsilon naught. If the area of each surface is A, there are 6 such surfaces. So 6A will be the area into E will be given by q upon epsilon naught. So I will get EA, which is the flux through one surface, will be q upon 6 epsilon naught. Now in this, the second part is what will be the flux through one of its face if charge is placed at one of its corner. You see now in this, I have now, you can see that there is a red cube. I have placed the charge at one corner. So to bring it to the same type, to bring it to the same question, because Gaussian surfaces are hypothetical surfaces. So I can make any surface. I can place this at the center and make a bigger cube. Make a bigger cube by adding cubes, like I have added 4 cubes on each face. So when I have added this, you can see it has come at the center. So each face will have 4 such cubes equal to the area of the original cubes. 4 such cubes. So each face has an area A, and A. So like this, there are 6 such faces. There are 6 such faces. So adding all, so hope you must have understood from this that there are 4 faces. There are 4A on each face. There are 6 faces. So the total area will be 24A, where A is the area of the small cube at the edge of which the charge is being placed. So I am again using the Gauss's law. E dot ds is q upon epsilon naught. E dot ds is q upon epsilon naught. E is taken out. Total area is 24A. So EA will be Q upon 24 epsilon naught. So you can understand from each face of the cube, the electric field will be Q upon 24 epsilon naught. So there are other ways which are given in the textbooks to solve this. You can use them also to solve the problems, but all of them will use the fundamentals of the Gauss's law. So we will cover many more examples in our detailed lectures, or if you connect through with me through the app, you will get more detailed answers of the various problems which are associated with with Gauss's law. Hope you would have understood Gauss's law. Thank you. We will cover many more topics in our